What if the biggest bottleneck holding back artificial intelligence isn't a lack of computing power, but rather the sheer exhaustion of human labor and the inefficiency of our current models? Imagine a world where AI could instantly understand complex scenes without us manually labeling every single object. Or where generating high-quality images happens 10 times faster without losing any detail. This is not a distant dream. It is the reality emerging from two groundbreaking studies released this week that are reshaping the creative frontier of generative AI. Welcome to a deep dive into the future of machine intelligence, where we explore how new frameworks are finally breaking the shackles of manual annotation and computational slowness. Today, we are unpacking two revolutionary papers, InstanceControl and MrFlow. You will learn how these innovations are moving the field away from rigid, monolithic systems toward flexible, modular architectures that can adapt on the fly. We will see how machines are learning to read text to understand images, and how they are mastering the art of speed without sacrificing quality. Stay until the end because these findings don't just improve algorithms. They unlock the potential for AI to operate in real time within our hospitals, our cities, and our daily lives. For decades, researchers and engineers have faced a stubborn dual challenge that has slowed the deployment of generative AI. On one side, we have the problem of semantic confusion. When AI tries to generate or analyze complex scenes filled with multiple entities, it often struggles to distinguish between them without explicit, labor-intensive instructions. Think of a busy street scene. Without human annotators drawing boxes around every car and pedestrian, the machine gets lost in a sea of pixels, unable to grasp the relationships between objects. This attribute confusion creates a massive scalability barrier, forcing teams to spend countless hours manually labeling data before any model can even begin to learn. On the other side, there is the issue of computational inefficiency. Traditional methods for generating high-resolution images are incredibly slow, requiring heavy computing resources that make real-time application impossible. Whether it is diagnosing a medical scan or navigating an autonomous vehicle, the lag caused by processing high-frequency details creates a dangerous gap between what AI can do in a lab and what it can do in the real world. We have been forced to choose between speed and accuracy, a compromise that no critical industry can afford. But now, a paradigm shift is occurring thanks to two distinct breakthroughs that tackle these problems head first. The first discovery comes from a framework called InstanceControl, which eliminates the need for manual labeling entirely. By leveraging advanced vision language models, this system can automatically parse textual descriptions and predict instance masks within visual conditions. Essentially, the AI can now read a sentence like "a dog sitting on a couch" and instantly identify the dog and the couch in an image without anyone ever drawing a box around them. It uses an adaptive refinement strategy that dynamically corrects noisy predictions using confidence scores, achieving a level of fine-grained control that was previously impossible without human intervention. This unblocks the scalability of multi-instance image generation, allowing engineers to deploy adaptable AI in dynamic environments where distinct characters coexist without requiring task-specific retraining. Simultaneously, the second discovery, MrFlow, addresses the speed limit of image generation. This approach introduces a training-free, multi-resolution pipeline that cleverly decouples structure preservation from detail correction. Instead of trying to solve everything at once, MrFlow utilizes rapid low-resolution sampling, followed by pixel space super-resolution via a lightweight pre-trained network. This orthogonal decoupling enables high-frequency resampling with a staggering 10 times speedup. The most shocking result is that this massive gain in speed comes with only a 1% quality gap compared to native high-resolution sampling. It proves that we do not need to sacrifice fidelity for efficiency. By separating the structural backbone from the fine details, we can accelerate diffusion models to speeds that make real-time application finally viable. The implications of these findings extend far beyond the laboratory, fundamentally altering the landscape for research, engineering, and society. For researchers, the removal of manual labeling barriers opens new avenues for exploring complex datasets in fields like bioinformatics and historical archives, where the cost of annotation previously made analysis intractable. We can now ask questions about data that we simply could not afford to answer before. For engineers and clinicians, MrFlow's dramatic acceleration offers a viable path for real-time applications in medical imaging and autonomous driving, where latency and bandwidth are critical constraints. No more waiting for batch processing when split-second decisions are required. Societally, these efficiencies accelerate the integration of AI into regulatory frameworks, providing robust, scalable tools that can handle diverse data formats without constant human intervention. We are moving AI from the realm of experimental validation to enforceable infrastructure. The field is converging on hybrid, decoupled architectures that separate semantic understanding from computational execution, challenging the old assumption that high-fidelity generation requires exhaustive, task-specific fine-tuning. Instead, we are building systems that leverage pre-trained foundation models as pluggable components to solve specific bottlenecks, creating a more robust and deployable intelligence. In conclusion, today's research highlights a decisive shift toward modular,